Hey everyone, have you ever looked at a solar panel and just wondered? It's this flat, dark rectangle that just sits there. No moving parts, no noise, and somehow it makes electricity. It feels like magic, right? Well, today we're going to pull back the curtain and break down the incredible science of how solar panels turn sunlight directly into power.
I mean, it's a really good question when you stop and think about it. There are no gears turning, no steam, no fire, nothing. So how in the world does this completely solid object take pure light and turn it into electricity that can power everything from a tiny calculator to an entire city? That's the mystery we're diving into today.
And you really do see them everywhere now. They're on our garden lights, they're on our calculators, you see huge arrays on top of homes and businesses, and they're even powering our satellites out in the cold, empty darkness of space. It's a technology that is scaled up from something you can hold in your hand to something that powers our entire world.
So, to really get to the bottom of this, here's how we're going to break it down. We'll start with that feeling of everyday magic, then we're going to zoom way in, right inside the solar cell itself. We'll talk about a secret ingredient called doping, then see how the cell builds its own engine. After that comes the aha moment, when the light finally hits. And to wrap up, we'll see how you go from one tiny cell to powering a whole city.
Okay, so let's start with the big picture. The whole thing hinges on a concept known as the photovoltaic effect. It sounds complicated, but it literally means light voltage. It's this amazing property of some materials that lets them convert particles of light, photons, directly into an electrical current. It's a super elegant process that happens at the atomic level.
All right, time to zoom in, way in. At the absolute heart of almost every single solar cell you've ever seen is the second most common element on Earth, silicon. And believe it or not, the journey to create this piece of high-tech wizardry, it all starts with plain old sand. Now, you can't just go to the beach and scoop some up. This sand has to go through a crazy intense process. First, they melt it in a super hot furnace to get raw but still messy silicon. Then, that silicon gets melted again and is cooled down very carefully to grow these huge, perfect crystals called ingots. Finally, they take those pure silicon ingots and slice them into paper-thin discs called wafers. That's the foundation for our solar cell.
So, why all the fuss about silicon? Well, it's because silicon is what we call a semiconductor. That means it's not a great conductor like copper, and it's not a great insulator like rubber. It's in this perfect sweet spot in the middle, which means we can tweak it to control how electricity flows through it. But here's the catch. Pure silicon all by itself is actually pretty boring. It doesn't do much. To unlock its power, we have to get a little creative.
And this is where the real genius comes in. It's a process called doping, and it is the secret ingredient, the absolute key that turns a boring slice of silicon into a machine that generates electricity from light. Doping sounds a little dramatic, doesn't it? But it's an incredibly precise, almost surgical process. Scientists intentionally sneak in a tiny number of atoms of a different element, an impurity, into that perfect silicon crystal. We're talking like one impurity atom for every 100,000 or so silicon atoms, but that tiny change is enough to completely transform how it behaves electrically. And to make this all work, we create two different flavors of silicon. On one layer, we add phosphorus. Now, silicon atoms have 4 electrons to make bonds with their neighbors. Phosphorus has 5. So when it slots into the silicon crystal, that 5th electron is just kinda left over. It's a free, mobile negative charge. We call this N-type silicon. For the other layer, we add boron, which only has 3 electrons. This creates an empty spot, an absence of an electron, that we call a hole. And this hole can move around just like a positive charge. And you guessed it, we call this P-type silicon.
So now we have our 2 special types of silicon. N-type, which is full of extra electrons, and P-type, which is full of extra holes. On their own, they're pretty neat, but when you press them together, oh man, something amazing happens automatically. They create their own built-in engine.
The instant these 2 layers touch, it's like a party. The free electrons on the N side see all those empty holes on the P side, and they just rush across the border to fill them up. Now, this chaos only happens right at the boundary, creating this middle zone that's now empty, or depleted, of any free-moving charges. But look what's left behind. The atoms on the N side that lost an electron are now positively charged, and the atoms on the P side that gained one are negatively charged. This separation creates a permanent, powerful electric field right across that junction.
This special boundary area is called the PN junction. And this junction, with its built-in electric field, is the absolute heart and soul of the solar cell. It's the engine, all set up and just waiting for a key to turn it on.
And that's a perfect way to think about it.
This field is like a very strict bouncer at a club. It creates a one-way street. It stops any more electrons from casually wandering from the N side to the P side, but, and this is the important part, it's perfectly set up to powerfully push any new charges that appear inside that field in a very specific direction.
Okay, so the stage is completely set. We've got our PN junction, we've got our one-way electric field just sitting there, waiting. All it needs now is the final ingredient, sunlight. This is the moment where it all comes together.
It all starts with a single photon, a tiny particle of light that has traveled millions of miles from the sun. It zips through the top layer of the solar cell, and bam, it smacks right into a silicon atom that's sitting inside that special depletion region we just built.
That photon delivers a little packet of energy, and it's just enough to knock an electron right out of its cozy bond with the atom. And in that one instant, we've created a brand new pair of charges that weren't there a second ago. A free, mobile electron and the mobile hole it left behind.
Now here's the magic. Before that new electron and hole can snap back together, that powerful electric field we talked about kicks into high gear. It acts like a sorting machine, instantly grabbing the negative electron and shoving it over to the N side while pushing the positive hole over to the P side. It forces them apart and keeps them apart.
And that is the photovoltaic effect in action. As billions and billions of photons do this every single second, you get this massive buildup of electrons on the N side and holes on the P side. This separation, this pileup of charges, creates a voltage, just like in a battery. And if you connect a wire from the top to the bottom, all those electrons have a path to flow, and that flow of electrons is what we call electricity.
That whole process happening on a microscopic level is just incredible, right? But a single tiny solar cell doesn't produce a whole lot of power. So the final piece of the puzzle is figuring out how we get from that tiny spark to something truly useful. Time to zoom back out.
A typical silicon solar cell, and it doesn't matter how big or small you make it, only produces about half a volt of electrical pressure. I mean, that's less than a single AA battery. So to power, anything, we're going to have to string a bunch of them together.
And we do that in two basic ways. If you connect the cells in a chain, one after the other, that's called connecting in series. When you do that, their voltages add up. So 36 cells at half a volt each gets you about 18 volts. Now, if you need more flow, more current, you connect those chains side by side, or in parallel. That makes the currents add up while the voltage stays the same.
All those carefully connected cells are then packaged up into the solar panel we all recognize. It's like a protective sandwich. You've got strong glass on top with a special coating to stop light from reflecting away, those little metal lines to collect all the electrons, and then layers of a special plastic and a tough backsheet to protect those delicate cells from rain, hail, and heat for decades.
So there you have it. From a humble grain of sand to a global power source, the solar panel is just this beautifully elegant piece of physics. It's a solid-state engine with zero moving parts, powered by light itself. The science is just incredible. Which kind of leaves us with one final thought, right? Knowing how this works, what do you think the next big leap forward is going to be to make this amazing technology even better?